Hello everybody, get ready to do lesson 2.7 part 2 of pre-calculus math today. And if you need a classwork sheet or homework sheets, email me here, animatedpowerpointmathvideo at AOL.com. Or if you need note-taking guides or any other course material, email me there. 2.7 part 2, you got nothing going into your notebook for this lesson, and you got 50 points here for your classwork. So teachers, today's bell work is simplifying exponential expressions here. Give your students about 3 minutes for this. Okay, welcome back students and teachers to today's bell work. And for 99 here, x over 8 to the negative 3 power. That will become, you reciprocate this in here, and then you cube it, and then you get 512 over x cubed, and then 4x squared quantity to the negative 2 power. You reciprocate it, and then you square it, and you get 16x to the 4th power, 1 over 16x to the 4th power for 1. Let's jump right into another example here on our first slide, first page here, sketching the graph of a rational function. Sketch the graph of f of x equals x over x squared minus x minus 2. So factor the denominator first step more easily so that you can find the zeros of the denominator. It's a quadratic, so this becomes x plus 1x minus 2. So now you can find your zeros, 0, 0, because f of 0 equals 0. So when x equals 0, y equals 0. So we know this is your y-intercept here at the origin. And then your x-intercept is 0, 0. Okay, so moving on to graphing this rational function. The vertical asymptotes are x equals negative 1. And then x equals 2, and then the zeros of the denominator, which is negative 1 and 2, that's why the vertical asymptotes. Horizontal asymptote, y equals 0 because the degree of the numerator is less than the degree of the denominator. And then additional points, you form a table here for x and f of x, and when x equals 1, y would equal negative 0.5 down here, so you have something that goes like this. And then when x equals negative 1, it's undefined here. But between negative 1 and, negative 0.5, it would be 0.4. So negative 0.5 would be here. So this gives you kind of an idea here. And when x equals 1, y is negative 0.5. So you got something that crosses over there and comes over here. And then negative 3, negative 0.3. and etc. like this here. This is what it would look like. This is what your graph will look like. You have this is actually inside of here, inside of these bars. But anyway, it goes like this. You have a part of the graph that decreases here. Another part of the graph that decreases to the y equals 0 asymptote, which is the x axis. Over here, that's an asymptote as well. But this part of the function crosses the x-axis, and it stays inside your vertical asymptotes here, like that. Okay, let's sketch one of these. We got 3x over x squared minus x minus 2. And then, so how would we do that? So, first of all, we can factor our denominator. These are our zeros here of our denominator, which are our vertical asymptotes. Our intercept here is through the origin. When x equals 0, then y will equal 0. That is a y-intercept there. Then vertical asymptotes are x equals negative 1, and then 2, again, negative 1 and 2. Then the horizontal asymptote is y equals 0. And then there's your table for that. Table of values, 0, 0. And then the graph of that would look like this here. So you have this decreasing here, and then again this is decreasing like that, and then this is decreasing like that, using your x-axis as an asymptote, and then here are your horizontal asymptote, and then these are your vertical asymptotes here. Inside your asymptotes, the graph decreases like this. To another example here, sketching a graph of a rational function. Now we have a little bit more complicated rational function, x squared minus 9 over x squared minus 2x minus 3, factoring the numerator and denominator. So this will become an x minus 3, x plus 3, then x minus 3, x plus 1. These cancel out. So that leaves us with x plus 3, x plus 1, x cannot equal 3 here. In this situation here, x cannot equal 3, because that would make the 0 times these, and that would just make it undefined. So our y-intercept is 0, 3, because f of 0 would equal 3. So when x equals 0, y would equal 3. So there's our y-intercept there. And then our x-intercept is negative 3, 0, because x plus 3 equals 0 when x equals negative 3. And then the vertical asymptotes would be x equals negative 1. So we have one vertical asymptote here. We have a point over here, simplified denominator. So make sure you factor your expression before you start finding asymptotes. So negative 1 is a vertical asymptote. Then we have a hole in the function, 3 and 3 over 2. F is not defined at x when x equals 3. So, and then y equals 1 becomes, because degree of n of x equals the degree of d of x. So we take the coefficient, which is a positive 1. So we have a horizontal asymptote here of y equals 1. So additional points, we produce a table for that. And we have stuff here where it's undefined at 3 when x equals 3. That is this hole up here. When x equals 3, at 3 over 2, it's undefined here. So when x equals 3, y is undefined. F is not defined at x equals 3. So what would the graph look like? It would look like this here. So you would have your upper part decreasing and to your horizontal asymptote at y equals 1. And then y equals 1 again would be your upper asymptote for this part of the function, and then it decreases here against the vertical asymptote of x equals negative 1. So it would be a partitioned like this here, not like a not like two vertical asymptotes, just one vertical asymptote. So let's try one of these now. X squared plus 3x over x squared plus x minus 6. So, and then this goes on your class worksheet. This is what you're seeing on your class worksheet. Now, to solve this, x squared plus 3x, we need to do some factoring. So, we can factor out on x, which is x plus 3, x times x plus 3 over x minus 2, x plus 3. These are going to cancel. So now we're left with x over x minus 2. So an x cannot equal negative 3 down here. Up here, it wouldn't be, I mean, that would be okay, but down here it's definitely not okay. So x cannot equal negative 3. And so here is a table of values for this function here. And then our intercept, when x equals 0, y would equal 0 here. It's because 0 times quantity inside here. So you have 0 in your numerator, and that's just going to make it 0. So 0, 0 is an intercept. And then a vertical asymptote, x equals 2 here, so that would be a vertical asymptote. That would make your denominator 0, so that's why that's a vertical asymptote. And then a horizontal asymptote is y equals 1, because this is the same degree as that. and then the coefficient of this is positive 1. So your horizontal asymptote of y equals 1. So what would that graph look like? They want you to graph these as well. There is a hole at x equals negative 3. So negative 3 would be about over here. I'm sorry. X equals negative 3 over here. So you have a discontinuation here in your graph there. And then otherwise it would look like your classic rational expression here. So, and then again, at x equals 2, that's your vertical asymptote. Your horizontal asymptote is y equals 1. Let's try another one. Publishing, we have a word problem here. A rectangular page is designed to contain 48 square inches of print. The margins on each side of the page are 1.5 inch wide. The margins at the top and bottom are 1 inch deep. What should the dimensions of the page be so that the minimum amount of paper is used? So, okay. So let A be the area to be minimized. So the area here, area is x plus 3 and then y plus 2, because we're going to use this as our x axis down here, and we have x plus 3 here. This is the area that we want to print, where our print will be. And we have 1.5 inches on each side, so that's going to be x plus 3. And then y plus 2, because y is our vertical axis. We have a 1 inch margin on each side of that. So the printed area inside of margins is modeled by 48 equals x times y. So up here in the problem, we need 48 square inches of print. So we get, well, 48 will equal x times y, or y, and we solve for y, be 48 over x. To find the minimum area, rewrite the equation for A in terms of just one variable by substituting 48 over x for y. So when we do that, we can put it into one variable. So up here, we have x plus 3 and then 48 over x plus 2, because that takes place over y. And then when we multiply these two together, we get this thing here. X plus 3, 48 plus 2x over x, and x has got to be greater than 0. We don't want this to be 0 or anything, or negative either. We don't want a negative area. So now we got a formula for our area in one variable. The graph of this rational function is shown. When you punch this into your graphing calculator, you get this here. And then when you hit minimum, you'll get this area, you'll get this point here as your minimum of this curve here. Because x represents the width of the printed area, you need to consider only the portion of the graph for which x is positive. Using the min feature of a graphing utility, you can approximate the minimum value of A to occur when x equals 8.5 inches. The corresponding value of y would be, now we solve for x, so 48 divided by 8.5 be 5.6. So the dimensions should be x plus 3, in this case here, x plus 3, it would be 11.5, and then by y plus 2, which would be 7.6. So we figured out that y is 5.6 here. Let's try another one of these publishing problems here, and this goes on your class worksheet. So let's take a look at our. Okay, we got a situation here where a page that is x inches wide, x inches wide, and y inches high, x times y, contains 30 square inches of print, which is right here. The margins at the top and bottom are 2 inches deep. 2 inches deep up here, and the margins on each side are 1 inch wide. So these are your side margins. Show that the total area A of the page is given by this equation here. Area equals 2x times 2x plus 11 over x minus 2. So when they're talking about the page, they're talking about this area here. And it contains 30 square inches of print. So the area here is xy, and x minus 2 x times x minus 4 equals 30. So that is basically your expression to show the area here of the print. And then when you y minus 4, you continue to like simplify this. Y minus 4 equals 30 over x minus 2. And then continuing now to solve for y equals 4 plus 30 over x minus 2. And then to include the 4 into this denominator, it becomes 4x plus 22 over x minus 2. Now we're trying to get back to here, remember? So thus area equals xy equals x times 4x plus 22 over x minus 2, because this is our y dimension here, then here is our x here. So when we factor out a 2 up here in our numerator, we get 2x plus 11 over x minus 2, and sure enough, we can simplify it back into this original expression for this area here. Determine the domain of the function based on the physical constraints of the problem. So we don't want our we do not want our denominator negative. So the margins on the left and right are 2. So x has got to be greater than 0. It can't be negative or 0. So it has to be greater than 2. Okay, so we're going to use a graphing utility to graph the area function for the work that we just did, to find the expression, to minimize the amount of area, verify your answer numerically using the table feature of the graphing utility. So the graph that we came up with is right here. Here is your graph here, and your minimum, it obviously looks like it's there. And the minimum is when x equals 5.87, y is 11.75, which will be about there. I'm going to let you come up with your table and put in your table values there for it to show that the table will coincide, of course, with your graph. To find your minimum by using your table, set your y values to equal 0.1, and it'll come up better that way. And that is your lesson today for pre-calculus math. Email me here for questions or materials. Thank you.